Okay, welcome to Chapter 5. As you see, it's bisectors of triangles. But before we talk about the bisector of a triangle, we're going to just talk about bisecting a segment. So let's just say we had a segment from here to here. And if I asked you, now segment has a beginning, it has an end, we'll just stick endpoints on there. If I asked you to bisect it, you can bisect it with several different things. You could bisect it with a point. You could bisect it with a line segment. You could bisect it with a line. You could even bisect it with a plane. We'll probably stay with line segments and lines when we talk about the bisector of a triangle. But the first thing, in order to bisect it, that prefix bi means you're going to break it into two equal parts. And that's what we want to do. So in order to break it into two equal parts, what do you think I'm going to have to find here? I'm going to have to find the midpoint. And the midpoint looks like it would be about right here. So I'll put a midpoint right here. And what we're going to do is we're going to bisect this line segment. And so you could bisect it all kinds of ways. You could bisect it like this. Okay, any line or any line segment that goes through the midpoint is going to bisect this blue thing right here. So if I called this, let's make this blue. If I call this line segment AB, and if I said this yellow line right here bisects line segment AB, we'll call that M for the midpoint, then what could you say about AM and BM? Well, we could say that they're equal to each other in length. So this would be a bisector. You could make this a line, you could make it a ray, you could make it a line segment, all right? Any of those things will bisect another line segment. Now, can you bisect a line? What if AB was a line? Could you bisect it? Well, no, you can't, because a line doesn't have a beginning and doesn't have an end. So there's really no midpoint to a line, but there is a midpoint to a line segment, and that's what the midpoint would be right here. Broke it up into two equal segments. So we could have all kinds of different lines bisecting this blue line if we wanted to. We could have another one that's maybe going like this. Okay, that would bisect it. Why? Because it hits it at its midpoint. What if I took this red line and put it right here? Is it bisecting AB? No, it's not bisecting AB because it doesn't hit the midpoint. It's got to hit at the midpoint. So it bisects it. We're going to take this a step further. Let's keep the blue one there. Let's get rid of the yellow and the red one. Let's get rid of all that. What we're going to do now is we are going to talk about a perpendicular bisector. Let me write that down. Oops, if I could spell it right. Let me see. Okay, perpendicular bisector. Now, this means it's going to do two things. We just talked about what it means to bisect. It splits this segment into two equal segments, so AM and BM would equal each other, but this time it says it's a perpendicular bisector. So there's really only one way that I can draw this new bisector. Remember, I had the yellow one and the red one. I could have all kinds of different colors in there bisecting this line segment, and they would all be segment bisectors. We would call it a segment bisector since we're bisecting a segment. But if I said a perpendicular bisector, it would specifically have to be perpendicular to that AB. I'm just going to eyeball it here and bring it down like this. Okay? And if I put a right angle there, that means this yellow line, or it could be a line segment, but this yellow line right here, if it's perpendicular to AB and it goes through the midpoint of AB, then this yellow line, right, we'll call it line L, then line L is the perpendicular bisector of line segment AB. Why? Because it does two things. It bisects it, which means it hits the midpoint, and it's perpendicular to it, and you know it's perpendicular because of this right angle symbol. And how do you know it bisects it? Well, because this has a tick mark and this has a tick mark. That means it's bisecting it. That's very important, what we're going to do here in a little bit. All right, so it's perpendicular bisector. That's a really important thing to know. And there's a theorem, a couple theorems that deal with perpendicular bisectors. We'll look at that here in a sec. Okay, here's a situation right here where, again, I have a perpendicular bisector. I just kind of set it up horizontally and vertically right here. But this theorem is called the perpendicular bisector theorem. Okay, pretty good name since that's what we're talking about, perpendicular bisectors. Perpendicular bisector theorem. Okay, I think I spelled that right. Perpendicular bisector theorem. And what does that say? Well, I'm glad you asked because I'm about to tell you. What it says is basically this. It says if you have a point on the perpendicular bisector, now which one is the perpendicular bisector? Well, it would be the yellow one because it's perpendicular to the blue one and it bisects it. How do you know it bisects it? Because it splits it into two equal segments. So AD, that's a D, AD and BD are equal to each other. So the yellow one is actually the perpendicular bisector. So what does this say about the perpendicular bisector? Well, it says this. If I take any point on the perpendicular bisector, so I could put a point anywhere on that yellow line. Let's just put it right here. Go to places any. Now watch what happens. If I take this perpendicular bisector, or a point on the perpendicular bisector, and I take it to the end point, okay, of the segment that we're bisecting, take a wild guess what could possibly be true about those two segments right there. Well, I think you're right. You probably figured it out. They are equal to each other. Absolutely. Okay, so they would be equal to each other. If you look at it, it's pretty easy proof on this because if these two sides were given equal, these two are right angles, this little part from here to here would be equal because of reflexive property. So look what I have. I've got side, angle, side. These two triangles are congruent. That means that these two sides right here must be congruent because of CPCTC. Corresponding parts are congruent, triangles are congruent. All right, so that's kind of a nice way to prove the perpendicular bisector theorem. And that's what it says. I could take any point. Let's take another one. Let's do this in a different color. Let's take another point. We'll make it a little bit lower, about right there. Okay, and what if I did this? What if I took it to this end point? Now remember, we got to take it to the end points. And we take it to this end point right here. Okay, what do you think is probably true about these two purple lines? Yeah, they look equal to each other as well. I could keep doing this forever if I wanted to. Don't want to. But you could see that a point on the perpendicular bisector, what they say, it's equidistant, it's the same distance to the endpoints of that original line segment. That theorem can be found on the bottom of page 322. Page 322 in our book, and it writes it all out. Okay, and you can read it word for word, but that's basically the description of the perpendicular bisector theorem. Now watch this. This also has a converse. Let's just talk about the converse. You can read it yourself, but the converse says if, now remember what the first theorem said. It says if this is a perpendicular bisector, then these two segments are congruent to each other. Let's get rid of this one and this one so we don't make it too much of a mess. All right, so our original perpendicular bisector theorem said if a point lies on the perpendicular bisector, then it's equidistant from the endpoints. What does the converse say? The converse says if the distance from, how do they say this? It says if a point is equidistant to the endpoints of a segment. So if you have a point on here, and if it's equidistant to this one, and it's equidistant to this one, you know what we should do? I wasn't going to do this, but I think it might be helpful. Watch, if I had a line right here, and if I had a point right here, and if I said that that point is equidistant from the endpoints of this segment, if that distance and that distance is exactly the same, guess where that point lies right here? That point must lie on the perpendicular bisector. So watch, that point must be on the perpendicular bisector of this purple line segment. So what does that mean? If this is equal to this, if those two are given to be equal to each other, guess where this point actually lies? It lies on a perpendicular bisector. So I could draw a line here. I know it's perpendicular, and I know that this and this are congruent to each other. So that's the converse of the perpendicular bisector. Let's do a couple examples, and we got a big major theorem we're going to talk about here in a sec. All right, here's a picture of the book. I figure it'd be the easiest way to do it instead of me drawing out. But let's take a look. It's real quick and easy. It says find each measure. It says find AB, which is right here. It's got a little bit of glare. I took a picture of it and put it on here. A little bit of a glare, but let's see what we want to do. We want to find what AB is. Well, what's going on here? Now, you might look at it and say, okay, well, that's 4.1. That's got to be 4.1. But let's understand why. point A lies on the perpendicular bisector, doesn't it? See, this is perpendicular to this because of the right angle, and it bisects it because BC and DC are equal to each other. What does our theorem say? Our theorem says that if a point lies on a perpendicular bisector, it's equidistant from the endpoints of the line segment. So watch, if AD is 4.1, it must be equidistant. A must be equidistant from D as well as B. So AD and AB must be equal to each other. If AD is 4.1, AB is 4.1. Pretty simple. Let's see what else we have. Make this a little smaller so we can fit it in our screen here. I think that fits, doesn't it? All right, let's take a look at this. Find WY. Well, let's come over here and let's zoom in so we can see it a little better. Where's WY? We're going to find this little part right here. All right, well, look at what's happening here. This is the converse of that theorem because we have a point X that's equidistant. It's given that XW and XZ are equal to each other. They're both 9. So it lies on a point that's equidistant from the endpoints of the segment. So if it's equidistant from the endpoints, what does it lie on? It lies on the perpendicular bisector, which means this line right here must be a perpendicular bisector. Well, it shows that it's perpendicular. We could have figured that out anyway, but it's perpendicular and it lies on the bisector. So that means that this whole bottom right here is split in half. That's hitting the midpoint. Y must be the midpoint. So WY and ZY must be equal to each other. And if ZY is 3, then WY is 3 as well. All right, I hope that makes a little bit of sense. Now, here's, they're always going to do this. They're going to do some algebra here. So what are they asking now? They're asking to solve for RT. So let's look at the geometry of it first, and we'll look at the algebra. We want to find what RT is equal to. Well, what is R? R is a point on a perpendicular bisector. It's perpendicular and it bisects. So that means these two are equal to each other. So the math is very simple. We've been doing that kind of stuff all year long. You can just look at it and go through it. You set them equal to each other and you solve for X. But it does say to solve for what? It doesn't say solve for X. It says solve for RT. So look, RT is 4X minus 7. So you've solved for X, and you plugged it into 4X minus 7, and you got 13. So pretty simple examples. Okay, now I just want to introduce a couple words to you. We've seen this a bunch of times before. Two lines intersect each other. There's the point of intersection. But watch this. If you have 2 or more, let's see, does it say 2 or more or 3 or more? Yeah, it says 3 or more. Okay, that's just a point of intersection of 2 lines. But watch this. What if you have 3 or more lines that intersect each other at the same point? We have a name for that, and I just want to jot that name down so that we are familiar with it. We call these 3 lines concurrent lines. Make sure I spelled it right. C-O-N-C-U-R, 2 R's, yep, I did. It just looked weird. Concurrent lines. So these 3 lines are called concurrent lines. Why are they concurrent? Because they all intersect at the same point. 3 or more, okay? 3 or more lines that intersect at the same point. They have the same point of intersection. We call them concurrent lines. Well, that point actually has a name too. And we'll put a little arrow right here. That point is called the point of concurrency. So we'll refer to that once in a while. So we just need to make sure our vocab is right and you understand that. Point of concurrency. Make sure I spelled that right. Wow, I killed that one. Let's try that again. I didn't even put the con in there. Just did the currency. How about this? Concurrency. There we go. All right, good thing I double checked that. That would have been embarrassing. All right, so we call that the point of concurrency. Now, what we're going to do in this, I'm going to switch to another program. It's a program I've just been playing around with. I've had it for a long time, never really used it. But I'm going to go to another program, and we're going to take a look at how all this stuff that we've been talking about, perpendicular bisectors and concurrent lines and point of concurrency, what that has to do with anything. All right, so we're going to go to our triangles. Remember, the title of this was Bisector of Triangles. We haven't even put too many triangles on here yet, so that's what we're going to do right now. So I'm going to go to another program, and we're going to hopefully, I'm kind of new at this, so bear with me, and we're going to try to figure out what's going on with this next theorem. Okay, what I'm going to do is this program allows me to draw a triangle, pretty cool, like this. Oops, missed it. There we go. and go back to here. So I've got a nice triangle. What I'm going to do is, hopefully, if I can do this correctly, I am going to do the perpendicular bisectors. Well, we did the perpendicular bisector of a segment, so I'm going to do the perpendicular bisector of all three sides of this triangle. All right, so hopefully I'll be able to do that. So perpendicular bisector. First thing I want to do is I want to bisect all three sides, which means I want to find the midpoint. So I'm going to click on here, and I've got a little thing, you can't see it, but let me find it, midpoint right there, and watch this. If I just click on this side, it shows me the midpoint. So that point right there is the midpoint. I click on this side and I got a midpoint, click on this side and I get a midpoint. Pretty cool. So now that's not my perpendicular bisector, at least I know where the midpoints are. Now what I have to do is I've got to make a perpendicular line that goes through this midpoint, and I got another tool up here that allows me to do that. So I am going to select this line. Now see what it did? It made a perpendicular. It's perpendicular to that line segment right there. And if I hover this over that point, see how it kind of snapped to that point? I click on it and there we go. So that is a perpendicular bisector. Unfortunately, that doesn't have the little right angle box there. It would be nice if it did, but it doesn't. But that is perpendicular. So now what I'm going to do is I'm going to come over to this side. See, it's perpendicular to this side. It's a nice right angle. I'm going to go to that point. That's a perpendicular bisector. They intersect right here. Now this is what we're talking about with the concurrent lines. Check this out. I'll click on here. I've got a perpendicular line, but if I put it right here, check this out. This is, to me, is kind of cool. All three actually intersect at the same point. I mean, it's not that big of a deal for two to intersect, because any two lines, if they're not parallel, will intersect each other. But to get three of them to intersect at the exact same spot, I think is pretty cool. Now, how did we do that? We found the perpendicular bisector. I wish I could write on here, but I don't think I can. I don't know. I might be able to. I have to figure it out. Not today, though. If I could write on here, I would write perpendicular bisector. Okay, I found the perpendicular bisector of all three sides. All right, that was cool enough that it intersects at one point right here, but that's not the coolest part. The coolest part about this is what I'm going to do right now. I'm going to take this point and I'm going to name it. If I remember how to do that, let's see, call that intersect. Okay, so I'm going to click on this and click on this, and it found the intersection of those two, and that would be the intersection of all three. And I'm going to actually, let's see, then I'm going to rename, and I am going to call this thing, here's our word, it's called the circumcenter. Circumcenter. And I can name it, which is kind of cool. Isn't this program neat? Took me a while to have the guts to practice using it, but, and let's put it about right there. All right, so that point right there is called the circumcenter. You say, big deal. Okay, it's a circumcenter. Oh, check this out too. Watch what this program can do. I can move this triangle around. And look what happens to the circumcenter. The circumcenter moves depending on how I move the triangle. Now watch this. So far, it's a this triangle right here, every time I'm moving it, it's an acute triangle. Watch what happens when I make it obtuse. Where's the circumcenter when I make this obtuse? It's outside of the triangle. That's an interesting concept right there. So if I have a triangle that is obtuse, the circumcenter is outside. It's in the exterior of the triangle. Look, I go back to acute. Where does the circumcenter go? It goes inside the triangle. Well, what other kind of triangle could I draw? I could draw a right triangle. So let's try to make this a right triangle. Check this out. That's a right triangle right there. Where does the circumcenter lie? It lies right on the triangle, but not just anywhere on the triangle. It actually lies on the hypotenuse, and not just the hypotenuse, but actually at the midpoint. Remember, these 3 points right here were midpoints? The circumcenter lies right on the midpoint, which is kind of cool as well. Now that's cool enough, but what I'm going to do, this is even a little bit better. Let's just kind of move this around a little bit. What I'm going to do now is I want to find a line segment. I'm going to create a line segment, and I've got a little thing up here, and you can kind of see it peeking through there. I want to do the segment between 2 points. So watch what I'm going to do. I'm going to click on this, and I'm going to click on this, and it gives me a line segment. I'm going to do the same thing with the other vertices. Notice where I'm going. I'm going from the circumcenter to the vertex. Do you see that? From the circumcenter to the vertex right there. And what's cool about this as well, if I can do this, you can't really see what I'm doing, and I should be, oops. See, I told you I was a little new at this. So let's do this. Let's click on this. If I hit Control, click on that, and I'm going to click on that. Good. And hopefully, I'm going to right-click here. I'm going to go to Object Properties, and I can change the color of it. Isn't that cool? There we go. And I'm going to make it actually a little thicker as well. Sorry for the delay on here. I guess I could have just paused this and done this, but it's kind of cool. I want to go to Style and just make it a little bit thicker. About like that. I'll close that thing out. All right, so then you can see it just a little bit better now. All right, so if I click on here, watch this. If I move this thing around, you say, okay, big deal. I went from the circumcenter to the vertices. But look at the lengths of the red lines that I just drew right there. Look at it. Does it look like they change? And even if I go outside of here, look at the red lines right there and right there. I wonder if I can move this thing around. Yeah, let's do this. Oops, made it kind of small. But over here on the side that you couldn't see before when I had it expanded. Let's see if I can do this. Oops, cancel that. All I got to do is move that over like that. I think we can see everything. All right, so there's the whole program. You can see what it looks like. Look at these red lines right there. It's actually G, H, and I, which they named it. It's those three right there. Look, they're all 5.1. Watch what happens when I move them around. Do you see the G, H, and the I over there? They stay the same length, which means what? Which means when you have a circumcenter, this is the circumcenter. What is true about that circumcenter? Well, what's true is that the distance from the circumcenter to the vertices, the distance from the circumcenter to each vertex is going to be exactly the same. So this length right here is the same as this length is the same as this length. It's not the original perpendicular bisectors, okay? It's just those lines right there. I could do this. Watch. I could, let's see. Yeah, I could hide these just so you don't have those in the way. Again, how did we make the circumcenter? We did the perpendicular bisector of all three sides, made our circumcenter, and what's true about that circumcenter, and this is the kind of stuff you're going to need to know in the problems, it's the same distance. So if they name this AB, right, from here to here, if they said that was 5 and they ask you what it is from B to here, then that would be 5 and this would be 5, okay? And as you see, it doesn't make any difference. Those are going to all be the same. Look over here with this G, H, and I. Okay, it doesn't matter how we move this triangle around, all three of those are going to be the exact same length. All right, so I hope that helps a little bit on circumcenter. We might cover that a little bit more in class because I want to do one more thing here. All right, I just thought of something before we go to the next topic. We call this the circumcenter. I want you to see why they call it the circumcenter. This is something I haven't done before, but with this program it makes it kind of easy to do this. Watch, I can go to the circle and I could go circle with center through a point. I'm going to click on this point right here. That's going to be the center of the circle. Watch, I'm going to take this out until I go to the vertices. See? Now, check this out. All three of these vertices lie right on the circle. Now, do they just lie on the circle because I made it a certain way? No, look, I can change this thing all around, and look, all three vertices actually lie on the circle. And here's my circumcenter. I had to make a new one because I closed it all out before, but, oops, sorry. Let's move this around right there. Okay, so if you look at this, this is called a circumcenter because the circle is around, it's the circumference, okay? It's, oh, there's a word I'm trying to think of and I forget. But anyway, it's called the circumcenter. Oh, circumscribed, right? This is a circle that's circumscribed about the triangle, which means the three vertices lie on the triangle. The circle is outside the triangle. The triangle is completely contained inside the triangle, or the circle, and the circle would be circumscribed about the triangle. All right, no matter how I draw it, I can't put those, look, I'm trying to put it outside the circle, I can't. All three of these vertices actually lie on the circle itself. So this is called the circumcenter, and that's why they give it that word, the circumcenter, because the circle is circumscribed about the circle. Let's talk about another kind of bisector, and this would be an angle bisector. And I think we've probably discussed a little bit about angle bisectors before, but let me just try to do this as quickly as I possibly can here. So let's put an angle right there, and if I had an angle bisector, okay, just like any bisector, it divides that thing into two equal parts. So this time we're bisecting an angle, not a line segment, where we're splitting this angle into two equal angles. If I went like this, those two angles that are formed right there would not be equal. If I went like that, they would not be equal. I want to split it, so I want to basically go down the middle, I guess people would say. But we want to split it so that both angles are equal to each other. If these two angles are equal to each other, then this right here is an angle bisector. Usually we say an angle bisector is a ray. All right, so an angle bisector is a ray because it has a starting point that starts right at the vertex and it keeps on going. That's the little arrow right here. So an angle bisector is a ray. Let's go over a quick theorem here about an angle bisector. Okay, here's the deal. We have an angle and it's being bisected, so this BF is an angle bisector. Well, our theorem says this. If I have a point, any point on this angle bisector, what's true about this point is it's equidistant from the sides of the angle. So we've talked about this before. What is the distance from a point to a line or line segment or even a ray? Okay, because the side of an angle is a ray. The distance is the perpendicular distance. So this is the distance from point F to this ray. I haven't named it, but whatever we want to call it. Let's just call this D. All right, so ray BD. So that's the distance from any point, from a point on the angle bisector, point F, to this point right here. That's the distance. All right, and what's true about it? Well, it's equidistant. So if I took the distance down to here, that distance is going to be exactly the same. Now, in this particular drawing, it may not look like it because I just kind of I divided this angle into two. I just kind of did it by sight. So these don't quite look exactly the same, but if this was a perfect bisector, if I measured it out and I bisected it, then these two line segments would look exactly the same. All right, so we call that the angle bisector theorem. All right, not much of a stretch. The angle bisector theorem. Let's put THM for theorem. All right, so again, what does it say? If we have a point on an angle bisector, it's equidistant from the sides of the angle. Well, the converse is true as well. Okay, if I have a point that's given that it's equidistant from the sides of an angle, guess where it lies? It lies on the angle bisector. All right, let's go back to that other problem, or that other program, and they have some examples. I'm not going to go through it just for the sake of time. Run a little longer than I wanted to, but on page 325, you can see that yourself. It's pretty much like what we did before on the perpendicular bisectors. I think you can figure that one out. So page 325, there's some examples and you should look at that. Let's go to the other program and talk about bisecting an angle inside a triangle. Okay, I'll try to go through this quick, but this is pretty important stuff. So let's draw another triangle. Okay, it could just be any kind of triangle like this. All right, so there's my triangle. What I want to do is do an angle bisector of all three of these angles. I want to bisect this angle. So in this program, I don't have to eyeball it. I don't have to just visualize what I think is being bisected. I can actually do it. So if I go over here, it actually has a tool that says angle bisector. And what I do is I just click on two lines and I've got a bisector. Now it gives me this perpendicular line right here as well. I don't need it, so I'm just going to take this and hide it. If I click that little thing, it hides it. And I'm going to do the same thing with the other angles. So I'm going to click on this one, and I'm going to get rid of that. Don't really need that one. I just care about the angle bisectors. And I'm going to do the same thing with this angle over here. I'm going to click on this side and this side. It takes that angle, and let's try it again. There we go. No, I didn't click on the angle bisector thing. There we go. Click on this one, click on this one. I've got the angle bisector. I don't need that line right there. Let's hide that one. There we go. So check it out. All three of these, they meet at a point. And I can move this around. Now remember the other one, the circumcenter? If I made an obtuse triangle out of it, look, that's an obtuse triangle right there. On the circumcenter, that obtuse triangle, the circumcenter was outside the triangle. But on this particular one, when I did the angle bisectors, that point, that concurrent point, right there, that point of concurrency, always stays inside. I don't care how I draw this thing. That point always stays inside in the triangle. Do you hear me? In the triangle. So we give that a name. And let's do this. I think that's the intersection point. Yeah, intersect two objects. So I'm going to click on this one and this one. It gives me a point. I'm going to rename it, and we will call the incenter. So it's not the circumcenter like we did before. It's the incenter. That's that point right there. It's in the center, okay, if you want to think of it that way. How did we get it? We bisected all three angles. Now, there's something special about that incenter right there, that point. That point is very special. And I'm just going to show you what it is. That point is equidistant from the three sides, or it's equidistant to the three sides of the triangle. That means the distance from this point to this side is the same as from here to here and here to here. How do we find the distance from a point to a line or a line segment? It's the perpendicular distance. So what I'm going to do is I have a little perpendicular tool right here, perpendicular line. It's going to get a little messy here, but just bear with me. We'll clean it up a little bit. All right, so I want to click on this point and this line, and it gives me a perpendicular line. That's kind of nice. What I'm going to do, I don't really need that whole entire line. What I'm going to do, actually, let's do this to all three of them. It's going to look really ugly, but we'll clean it up, I promise you. See, there's perpendicular. Do you see it? From this point, perpendicular to the line, and from this point, the incenter, to perpendicular to this line. So we've got all that. You're like, oh my goodness, this is crazy. Well, let's do this. Remember all those angle bisectors? Let's just get rid of the angle bisectors, or we'll just hide them so we don't see them anymore, just so it stays out of the way. We'll hide this one, and we'll hide this one. I just want to be left with these three things. Now, remember, how did we find the incenter? We found it by taking the angle bisector of all three angles. But what's true about this incenter? This incenter, the distance from this point to this side right here, okay, to the distance from this point to the side is going to be the same as the distance from this incenter to this side, from this incenter to this side. All three of those are going to be the same. So what I'm going to do, I can, let's see if I remember how to do this. I want to find the segment between 2 points. So I want to go from here to there, and I'm just going to make that thing right there. Now watch what I can do though. I can take that line and get rid of the line. I'm just left with that segment. I'm going to do that for all three of these. Again, what do I want to do? From, let's do this one again. I want to go from the incenter to the point where they intersect right there. All right. Yeah, I think I'm doing that right. And then get rid of that, and then go from, let's do this again. Yep, from the incenter to where they intersect would be right there. And now let's get rid of this line right there. Now, this is what I wanted to show you. These three distances are equal to each other. If I could write on top of this, which I can, I put little tick marks right here to show that those three are equal. But if you look over here off to the side, watch this. If I click on all three of these, it highlights, actually I didn't click on, oh I know, I got to hit the control button. Click on all three, there we go. Click on that one, and that one, there we go. Look at that. They called them lines N, M, N, and P. They're all exactly the same. Now watch when I move this triangle around. Look over here at this M, N, and P. Look at the lengths, right? I can make it smaller. It stays the same, It doesn't matter if I went obtuse, right? All three of those are going to be exactly the same, which I think is pretty cool. So how did we get that incenter? We did the angle bisect. We bisected all three of those angles, and we found the incenter. I got rid of those lines. I kept where the incenter was. And what's true about the incenter? It's the same distance to the sides of the triangle. So this distance, and this distance, they're all equal to each other, which is very, very important for what we're going to be doing on the homeworks and stuff, okay? Because if they give you the length of this is 5, then this is 5. Or if this is 3x minus 2, and this is 5x, minus 7, then what do? You set them equal to each other. You can solve for x, plug it back in, and you can find the lengths of the line segments. Let's do the circle thing, and then we'll be finished. Watch this. I can make a circle here. Actually, is that what I want? Yeah, it is what I want right there. Okay, watch. I'm going to use this as the center of the circle, and I'm going to take this out. Now watch. If I went to the endpoints, look, it doesn't hit all three like it did on that other one. Remember the first one we did with the circumcenter? It hit the outside, but it doesn't hit here. Where does it hit? It hits right inside the circle. Remember I talked about that before? Watch this. If I move it around, that circle is inside the circle. So we say that the circle is inscribed in the triangle. It's inscribed. It means it hits the three sides of the triangle just at that one point, but it's inside the triangle. It's the in center. The circle is inside the triangle. The other one, the circle, is outside, or it's circumscribed the triangle. Circumscribed means outside. So the circumcenter is outside the triangle, and the in center, the circle, is inside the triangle. Look, it doesn't matter how I draw this thing. The in center still stays inside the triangle, and the circle still stays inside the triangle. All right, well, I hope that helps a little bit. And I think this program, I think I did pretty well, don't you? On this program, it's the first time I ever used it. So you're the guinea pigs on this one. But hopefully I'll be able to use it some more. It does a lot of things. It's very powerful. I just have to learn how to use it. Okay, I'll be quiet now. I went over 30 minutes. Sorry, I try to keep these under 30. But I went a little bit long. But hopefully this made a little sense. And if you have some questions, obviously we'll go over it in class the next time we have class. All right, we'll see you then. Bye.